Hello, this is Brandon Cook. I am an M144 Calculus 1. We meet on Tuesdays and Thursdays at 12:45 to 2:20, and I'm going to be doing 2 questions. Okay, so let me pull up the question. So the first one is, a designer is making a box with a square base and open top as in figure 1. She wants to minimize the amount of material used for a tray. Will have a volume of 1200 centimeters cubed. The box is made by folding up the edges of a sheet of aluminum, as shown in figure 2. She wants to find both the minimum amount of material as well as the dimensions of the box with minimum amount of material. Okay, so let's draw a diagram. So this is question 1. So let's draw a diagram. So it looks something like this. And very rough drawing. So these are going to be the measurements. So this is what it would look like, and then it's going to, be folded up. That's what's going to look like when it's folded up. So what do we have, and what is given, and what needs to be optimized? So we're given that the volume is going to equal 1200. Sorry, I have 2 things up at once. Centimeters cubed. So and we're trying to find the material, which would be the area of the box itself. So we're trying to find area. So we're optimizing the area, and so the relationship would be the volume. So the volume equation, so it'd be 1200 equals x times x, so x squared times y. And then the area is going to be, so it's going to be the base plus each side, the area of each side. So the area of the base, which is x squared, this equals area. And then it's going to be plus 4, because there's 4 sides, xy, because it's y, which is the height, times x, which is the base. Okay, so next we're going to want to substitute in, we're going to substitute in we're going to do for y for this one. So it's going to just be divided by x squared divided by x squared. So it's going to be y equals 1200 over x squared. So we're going to just bring the equation down here so we have more room to work. So a equals x squared plus 4y times 1200 over x squared. Or sorry, 4x. Small mistake there. So now we're going to distribute this in, so it's going to be a equals x squared plus 4800 x, because this x and x squared, the square cancels out. Okay, so now we're going to want to take the derivative of this, so we're going to set it up so we can take the derivative, so it'd be a equals x squared. This would become 4800 times x to the negative 1. Okay, now we're going to take the derivative, which would be 2x plus negative 9600 x negative 2. So that would be 2x minus, 9600 over x squared. Okay, and now we're going to want to find the critical number, which for this we just have to solve for x. So we're going to set it equal to 0. And to make it easier, we're going to add 9600 over x squared over, so that's 9600 x squared equals 2x, and we're going to multiply each side by x squared. And that's going to leave us with 9600 equals 2x to the third. Now we're going to divide by 2, and x to the third equals 4800. Now we're going to take the cube root. It's x equals 16.869. There we go. Now that we found x, we're going to plug it back into the relationship equation to solve for y. So it's going to be, we're going to do it right next to it. 100 over what was x squared is now 16.869 squared equals y. You solve that out, you get y equals 4.217 centimeters. Okay. And so we tested, so for the endpoints, we're just gonna touch on this a little bit. For the endpoints of this graph, so because of this expression right here, it does not ever equal 0 on the first endpoint. It cannot equal 0, or it will be not solvable. So as it gets closer to 0, it's gonna get closer and closer, but it's never gonna actually touch 0. And then this one continues on for infinity. So the point that we just found is actually right here, which is the minimum amount of material that we're gonna use that maximizes the volume. So the minimum area for the same volume. And it wouldn't be one of the points over here because it continues off into infinity, which just results, same as here, in infinite area of y, or that would have been the y, that this would be infinite area of the base, which is x. Yeah, so, and then that's the 2 there. So the total material would be, we're gonna plug these 2 back in to this equation. Oh, sorry, I'm a little low. So that would be a equals 16.869 squared plus 4 times 16.869 times, sorry about that. Sorry about that also. Jeez, that was loud. Okay. Sorry, just a reminder from my calendar. Okay, so that means the area equals, when you solve all of this out, that would be 569.109 meters squared of material. Okay, now we're gonna do the second question. Number 2. Come on. There we go, number 2. So for the second question, we're gonna use a graph that represents R of t, the rate at which the volume of a spherical balloon is changing with respect to time. Here, we're gonna show you the graph right there. So that's the one we're going to be using to solve questions A through F. So I'm going to draw up the graph real quick. Sorry, this is a very rough sketch of the graph. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, so A, we want to find when the volume is increasing and when the volume is decreasing. So to do that, we just have to look at the graph. So for A, it's increasing from 0 to 1. So increasing equals 0, 1, and then it's also increasing from 6 to 8. So we can tell that it's increasing because the graph shows a positive slope, and the slope represents at which the volume is changing. So if the slope is increasing, that means the volume is increasing, and it's increasing from 0 to 1 and then from 6 to 8. Even though it is negative over here, it is still at an increasing slope. So decreasing it is from 3 to 6. So from 3 to 6, you can see that has a negative slope, which means that the volume of the spherical balloon is decreasing between those 2 points. Okay, so for B, at what time is the volume of the balloon decreasing most rapidly? Well, it's a good thing. There's only one point where there's only one section where it's decreasing, so that means that at that point it is decreasing most rapidly. So from here to here, negative slope. Sorry for the shakiness of this. It's not really the most stable stand I could make, but it's what I have. Sorry about that again. So and then from here to here, positive slope. Then from here to here, positive slope. All right, C. Find the volume of the balloon at t equals 1. So t of 1, t of 3, t of 5, t of 7, and t of 8. So once again, we're going to be using this graph, but in order to find the different areas, we're going to find the area under the curve to find the actual volume of the balloon at those points. So we're going to use geometry to solve these. So just marking off. So yeah, I'm just marking off different parts that we're going to use here. Okay. So to start out, we're going to solve the first triangle, which is up to 1. So that's 1/2 base times height. So base is 1, and it's up by 2. Suppose I didn't really. There we go. We're using these lines. Okay, so it is, that equals 1/2. The base is 1. That's times 2. So that equals 2 over 2. So that equals 1 inch squared cubed. Sorry. Now for number 3, we're going to do t of 1 plus base times height, because it's a square, which equals 1 plus, so the base of the square is, it's 2, and the height of the square is 2, so it's 2 times 2, that equals 1 plus 4, which equals 5 inches cubed. And then for 5, it's going to be t of 3 plus, so 5 from 3 to 5 is another triangle, so it's 1/2 base times height. Okay, and that would be, so it's the base is 2, the height is 2, so it's 1/2, 2 times 2 equals 4 over 2 plus 5, so that'd be 7 inches cubed. So for t of 7, it would be T of 5 plus, so till 7, it's another triangle, so it's 1/2 base times height. For this triangle, it's only, the height is only 1, but the base is 2, so it's 1/2 1 times 2 equals 2/2, which equals 1. Oh, sorry about that. Base just fell. Too much shaking. Sorry once again. But because it's a negative, so it'd be, so once again, we're gonna bring T of 5 over, so that's 7. But because it's a negative, it's gonna be -1, because the area of this curve is -1. So that's 6 inches cubed. And now we're gonna do T of 7 plus 1/2 base times height, which equals, so we're solving for 7 to 8. So the height is 1 and the base is 1, so it's 1 times 1 times 1/2, which equals 1/2 plus 6, which equals 6.5 inches cubed. So those are all the solved out ones. The reasoning, so the reason that this works is because integration is just finding the area under the curve, basically. And the area under this curve is the volume of the spherical balloon, because this is representing the change of that. So the derivative of the change, or the integral of the change of that, is the actual value of the volume. So we're gonna do letter D now, which asks us to write an integral that represents the volume of the balloon at t equals 7 seconds. So an integral of that would just be very simple. Integral from 0 to 7 of RT. So that, because the line is RT, taking the integral of that line between 0 and 7 would give us the volume at the point x equals 7. And then for E, it wants us to find the value of the integral you wrote for part D. In other words, find the volume of the balloon at t equals 7 seconds. You can use geometry to solve this. So we already solved this, actually. So we know that the in order to find that, T of 7 equals T of 5 plus 1/2 base times height, which is 1/2 1 times 2 equals 2/2, which equals 7 minus 1, which equals 6 inches cubed. So that is what equals T of 7. And now F, final question. When is the balloon at its maximum volume? The balloon is at its maximum volume. We can go back up here and look at T equals T of 5. So, oh, sorry. I just realized. Jeez, sorry for the stand. Let me zoom back out. It's a very poor stand. It's not the most stable. It's T, not X. Now that that's fixed, let's go to F. When is the balloon at its maximum volume? Well, if we go back up to the solved equations, we can see that the largest volume is 7 inches cubed. So we just write this out again. T of 5 equals T of 3 plus 1/2 base times height equals 1/2 2 times 2, which equals 4/2, plus 5, which equals 7 inches cubed. So the volume of the balloon is largest at t t of 5. Because if we integrate all of the points, we can find that. Okay. This is Brandon Cook. Thank you for listening.